everybody. Thank you so much for joining our webinar. We're going to talk about the Vulkan loader, have a deep dive into that. Our presenters are Mark Young and Lenny Como from LunarG. But before we get started, I want to do a little bit of housekeeping. First of all, this presentation is available for you to download. If you look at the little text icon or document icon, you can download the presentation there. Also, we are shooting video of this presentation, so you don't have to frantically take notes. You can just watch the video anytime you want. You'll get an email later today with the URL where you can go to download that. Also, we're going to answer questions at the end. If you have a question during this webinar, look for the question mark icon and you can enter the question there. Then we will read out those questions and answer them at the end. All right, so I'm going to turn this over to Mark and Lenny. Let me just take a moment.
All right, so as Kathleen said, thank you very much, by the way, Kathleen. This is the Vulkan Loader Deep Dive. And I just, first of all, wanted to say welcome. Thank you for spending the time to come and learn more about the loader. And I think that you'll find this beneficial, whether you're an intermediate or advanced Vulkan developer. You've probably heard of Khronos, but you're probably thinking to yourself, who are these people that we're listening to right now? So LunarG is a software engineering firm, and we've really focused on different graphics and shader technologies. And in terms of what we're talking about now, the primary focus here is Valve has provided us funding to support the Vulkan ecosystem. And we show that in several ways, one of which is the Vulkan loader, which we're talking about today. Other ways we do it are validation layers and various tools for Vulkan. And of course, we release a Vulkan SDK about once every month if you're interested. Who am I? I actually started out cutting my teeth in the game industry, but I've spent about 14.5 years writing various graphics drivers for ATI, AMD, and Qualcomm. And right now I'm the Vulkan desktop loader owner. I'm not one of the original architects, but I currently own the loader itself. And then my partner in crime here is Lenny Como, and he is currently the co-owner. And he has recently joined us about 6 months or more ago, and he comes from Cadence Design. One thing I'd like you to think about right now is, what do you want to learn from this presentation? I don't know about you, but as a friend of mine used to say, my forgetter works really good. And so if you have an idea of something you'd like to learn about the loader, write it down now, and if we don't cover it, that's perfect thing to cover in the Q&A at the end of the presentation. I want to cover some things first, like what is this not going to be about? This is not going to be about anything like an introduction to Vulkan or an analysis of why you should use Vulkan over OpenGL. The idea that we have is that you are already familiar with the basics of Vulkan. Now, if you are interested in any of those things, the highlighted yellow items here are links that you can use in the final PDF version of the presentation that's available. So you can feel free to peruse those after the fact. I would really recommend the Vulkan resources page set up by Khronos, because they have a ton of external items that are made available for you that could be of use to you at any point during, your Vulkan experience. But for those of you who, maybe aren't as familiar with Vulkan, don't just leave yet. I know some of you might be thinking, whoa, wait a minute, this has got no relation on me whatsoever. You actually might learn something useful for yourself just by paying attention to some of the possible optimizations we'll be covering. So, as I mentioned, what will we be covering? We're going to look at the loader and how it interacts with applications, drivers, and layers, as well as some debug settings you can use if you're having issues with the loader and you want to try to figure out what might be going wrong, if you want to force the loader to behave in a certain way, as well as we want to try to cover some optimizations. What are we talking about here? If you've written a graphics application before, in this case a Vulkan application, you know that you have your application and somehow it talks to the hardware. Usually it talks to the hardware through some kind of driver. In this case, Vulkan talks to the hardware through an installable client driver. or ICD for short. So you can see that in the blue area. Additionally, Vulkan has the concept of layers, which are allowed to expand or augment functionality Vulkan has. And so somehow your application gets access to either the ICDs or the layers it's needed, and really that's where the loader steps in. So as you can see in this diagram here, the loader is like the key gatekeeper through that collates all the information on the available ICDs on the system. So it goes out there, looks for any Vulkan drivers that are available. It looks for Vulkan layers that are available, and it makes those things apparent to your application. And that way, you don't have to do all the bookkeeping yourself. I'm going to refer to loader in the singular sense pretty much throughout this presentation. But in reality, there's actually two different loaders. And the reason why is Android has its loader, which is a closed source loader, and that loader is available starting with NuGet. In many senses, we'll call that the mobile loader. On the other hand, we have what's called the desktop loader, and that's what we're going to be mostly focusing on here. And that will cover the loader that supports Windows and Linux. The nice thing is we work very closely with the Google people. In fact, some of them on a regular basis. So what we've decided to do is define one interface design, which we have set up in GitHub, and both loaders strictly adhere to that interface design. And the majority of what we cover here is based on an interface design. So what you learn, with the exception of most of the debug features, is applicable to desktop or mobile. Unfortunately, Vulkan is not supported on Apple at this time. Apple has chosen to stick with its Metal graphics layer, so sorry, Apple guys. As I mentioned, we have this loader interface doc. We've decided to make it available, and so this document is pretty much going to cover everything we're going to talk about in this presentation, and then some. So a great place to come back, even if you choose to look through this presentation, you still have questions, is always go look at this document. This document is kept pretty much up to date with every loader release. It may lag a couple of weeks or so, but we really try to keep the information in this document as fresh as possible. So if you're always wondering about how an interface works, or if we do update an interface, it will be available in this document. Let's take a quick look. I don't know about you, my history is in OpenGL. I'm an OpenGL guy from day one when OpenGL came out from the Khronos, or from the R back then. Some of the frustrating things I found when I worked with OpenGL is on certain operating systems, they controlled the loader, but they would update it so infrequently. In fact, I think to this day, on Microsoft Windows, you might be restricted to OpenGL 1.5 perhaps by default, and you have to query everything else by extensions. And in some of those cases, the loader source for OpenGL isn't even available, and if it is, only certain people can contribute to it. Khronos has really decided to open this up, and the Vulkan loader is open source, and it's updated very frequently. We actually update it daily, but we release it in an SDK runtime package about once every 4 to 6 weeks. And if you're interested, feel free to submit bugs, patches, cherry picks, enhancement designs. The only requirement we have is there is a CLA if you contribute code. Now, where would you do that? Well, Khronos has made the source available on GitHub. And I don't know about you, but I'm super excited to finally work on an open source project. I've been working in companies on closed source projects for years, and there's a certain amount of gratification you get when you work on an open source project that many other people can build upon. The loader can get onto your system in many different ways. On Android, of course, it's going to become installed as part of your operating system, and that's going to be Nougat or newer. On desktop, you can get it in several different ways. I've mentioned here, you can get it through a driver package. NVIDIA, for example, installs a loader as part of its driver package. You could get it as part of an application. Certain Steam games install a Vulkan loader. You can get it as part of the LunarG SDK, or you could build it yourself from GitHub. One thing I really want to mention is just because you have a loader does not mean you have full Vulkan capabilities. In order to run Vulkan, you're going to need, as I mentioned before, a driver, hardware, and the Vulkan loader. It takes all those things combined in order for you to be able to use Vulkan. Now, you may end up having multiple copies of a loader on your system at one time. That's okay, and we'll kind of cover that in a few slides. And here's an example of multiple installs. So if you look at this, this is, a capture of actually Lenny's Windows system. And if you look close to the bottom, you'll see that there's two Vulkan runtimes installed, 10391 and 10420. You kind of sit there scratching your head, is this okay? Well, in this case, if you look above, you'll find that NVIDIA has a driver installed on the system. And to make sure that things behave properly, for Vulkan, for their end users, they've actually installed the 10391 Vulkan runtime. Now, how does that affect me when I go to use an application? Because there's multiple runtimes on your system, the way that our installs work is it attempts to find the most recent version of the Vulkan loader. So in this second bullet point list, you'll see two Vulkan loaders for Linux called libvulkan.so and then a version, and two Vulkan loaders for Windows called Vulkan-1 and an version. Now, what happens is that whenever we install, on Linux, we set up a symbolic link to the most recent one, and that symbolic linked file is called libvulkan.so.1. That is the file you should be linking against. Additionally, on Windows, we make a copy of the most recent one as part of the install. So in this case, we're going to copy the file vulkan-1-1042.0.dll, and we're going to rename that copy vulkan-1.dll as part of the install. And the idea is that the 1 indicates the ABI version, and so we will be, making sure that anything called vulkan-1.dll is backwards compatible. When we wrote the loader, the intent was to make it efficient, small, really optimized, and completely ignorant. So the loader just, does the basic information you want and gets out of the way, because we wanted to make sure that your application could execute as fast as possible. Of course, as many of you have heard in Spider-Man, with great power comes great responsibility. You can cause problems if you behave incorrectly, and the loader isn't necessarily going to save your butt. In fact, the loader will crash if you do something improper. Examples include using an extension you haven't enabled. If you query a device command, which we'll cover in a little bit, from a certain device, let's say NVIDIA, but you attempt to use it on a separate device, that will crash too. Additionally, if you pass in a Vulkan instance in place of a Vulkan device or vice versa, that can cause a crash. So you have to make sure you're careful. And I wanted to cover a few of the most expensive calls in a loader. The loader isn't, certain Vulkan commands aren't supposed to have the state associated with it. It's supposed to be able to actively query the underlying ICDs and hardware. But the loader really does need to record information so it can handle the appropriate physical devices and logical devices at runtime. Because of this, every time you call like a vk create instance, a vk create device, or any of the vk enumerate calls, there's a certain amount of processing that has to happen every time you call one of those. That can include regenerating arrays, reallocating, certain structures. And the reason why is, one reason, that there are now external GPUs you can plug into, for example, your laptop. So if you wanted desktop accelerated graphics, but at your laptop when you're at your desk, you can buy one of these external towers that house mostly a standard off-the-shelf desktop card. Other things include layers can actively come and go while you're running. The system could change from battery to plugged in and vice versa, and that may change the way certain things behave, like if Optimus, for example, is running. So I don't know about you. I grew up in Florida, and one of the scariest things for me was walking into the kitchen at 2 a.m. to get a glass of water, flipping on the lights, and all of a sudden having a 3-inch palmetto bug fly at my face. Nothing is guaranteed to make a man scream like a girl than this site right here. So let's just say no to bugs. So we've made certain debugging features available to the users of the loader. You can set up these environmental variables, in this case, vkLoaderDebug, and it will spit out to standard error various warning messages or error messages. You can choose what type of message you want. Typically, I use all because it doesn't spew that much information. Another way you can debug problems with the loader is by enabling validation layers. So I would recommend if you have a crash with the loader, try loader debug all and force on validation layers, and you should be able to diagnose the issue you're seeing. Now we're going to head deeper. We're going to cover some of the important topics on what critical portions of the loader and what decisions we've made based on those constructs. The first idea that the loader has, and even Vulkan, is called dispatchable objects. Each critical object in Vulkan has inherent to it a dispatch table associated. And in this first command, vkGetEventStatus, you can see that there's a vkDevice. The vkDevice is an example of one of these dispatchable objects. And what I mean when I say dispatchable objects is that when you step into the loader, you will see that that device is really a structure. And the very first item in that structure is a dispatch table. You can choose to create your own dispatchable objects in a layer or an ICD, but there's a little bookkeeping behind it because the loader needs to be able to generate the dispatch table for your new object. So if you created something like myQ, vkMyQ, or something that was internally handled that you needed to be dispatchable, you would have to register it. Again, I'm not going to cover it here. That's in the loader and layer interface doc. An important concept that you have to know about the loader and Vulkan is that there's an instance level objects and commands and there's device level objects and commands. When we say instance level commands, we're talking about high level. It's something that's in the instance level has to think about what all ICDs, what all physical devices are going to do. For example, enumerate physical devices. It's going to go grab every physical device out there and provide it to the application. On the other hand, a device level object is specific to one physical device and actually one logical device of that physical device. So you can see between the two boxes, colored boxes on the screen around the loader, the space that an instance object and a device object cover. Now we're going to talk about trampolines and terminators. Not these kind, as fun as that would be. In the case of the loader, a trampoline is the very first entry point for a command. So as the diagram at the bottom shows, you have an application, you have the first entry into the loader, which we call a trampoline. You may have some set of enabled layers, you have a terminator, and then you have ICDs. The trampoline at the beginning there is always there if you query a command through the loader. So if a loader actively exports a command, you're going to get a trampoline. If a loader is an instance command, you're always going to have a trampoline. So that trampoline is there the majority of time. On the other hand, the terminator at the end, as I mentioned, remember the difference between an instance and a device level object. For an instance object, we have to talk to all ICDs. That's the purpose of the Terminator. For a device object, you don't have to talk to all ICDs necessarily. So you can actually go right from layer C to the ICD, which we will show on the next slide. Or not the next slide, sorry. Before we get there, we're going to talk about a call chain. So a call chain we're going to refer to several times, and that's a sequence of calls. It may include the loader one or more times. It can include any layers you've enabled, whether implicitly or explicitly, and it can include one or more ICDs. There's a different type of call chain for a device object or instance object, and those are actually set up at vkCreateInstance or vkCreateDevice as appropriate. So now we get to the instance versus device call chain. So here's the diagram you keep seeing over and over again. You see the application triggering the loader trampoline, then it goes through whatever layers are enabled, then it hits the loader terminator and goes to all ICDs. As I mentioned, for a device call, you can drop that terminator because you're going directly to one ICD. There are certain device calls that can't do this. Usually, if it's the case where the loader has to translate something into the ICD interpretation of the object. For example, a VK surface KHR object was originally entirely controlled by a loader, but that's now been changed so that ICDs can control that as well. In that case, you would need a terminator, and it would look more like the diagram above. But for the majority, the vast majority of device calls, you're going to have a chain like this if you go through the loader. If the loader exports it and you call it, this is what it's going to look like. Now, this is what we recommend. If you have an application and you want the best performance completely whatsoever, what we recommend you do is for every device call, use vkGetDevice ProcAddr, even if it's already exported by the loader. The benefit is, if you look at it, if you use GetDevice ProcAddr, it skips the trampoline. The benefit also comes from if you don't have any layers enabled. What happens? Your applications is going to talk directly to the ICD via the function pointer return. And so if you set up your own dispatch table for all your device commands, and you query each command via vkGetDevice ProcAddr for your specific device, you're going to get the best performance. Another concept we want to cover is called manifest files. So just like a ship's manifest back in the day that listed crew, passengers, cargo, the intent of it was to provide some amount of security, to make sure that a ship wasn't unintentionally or intentionally bringing in contraband into the country. And on desktop, we use this concept, and then we have these manifest files. They're JSON formatted files that identify information about a layer or an ICD, and the loader uses that. The intent is to provide security. So the loader will go out, read these JSON files, and only load the final contents if the JSON file appears valid. In the case of layers, we still don't even load the layer until an application says, hey, I really want to load that layer during the vkCreateInstance. Now, Android, on the other hand, because their layers and ICDs are completely controlled, when they spin the operating system image for a phone, they have no use for manifest files. So you don't need to worry about this. But we'll still cover the ICD and layer manifest files in more detail in a little bit. What's exposed by Vulkan by default by the loader? So the loader is going to export certain symbols for you to use as a convenience. So you don't have to do get instance or get device proc address every time. That's going to be core Vulkan and a set of WSI functions or Windows System Integration functions. For now, Khronos has decided to make all the features that are platform specific in terms of Windows System Integration extensions, because they're not entirely certain yet this is the way they want to go. So they've left it as extensions with the idea of maybe pulling it into core once things settle down. So if it's something beyond core or these WSI extensions, how do I do it? Is there going to be any problems with the loader? Well, if the loader knows about an extension, there's known problems. Okay, yeah, I know, bad pun. On the other hand, if the loader doesn't know about the extension and it's a device extension, that's going to be handled automatically. And I'll show you again why that is. If it's an instance extension, there's going to be problems. And in order for you to properly use an instance extension, the loader really has to know about it. Here's why. So again, looking at the device call chain, if you have an extension that's a device extension, the loader doesn't know about it, you have to call vkGetDevice ProcAddr. When you do that, you're skipping the loader completely, as this top level image shows. On the other hand, the instance, if it's an instance extension, because it's an instance call chain, you call vkGetInstance ProcAddr, and it's still going to look like the bottom image. So it still needs a trampoline, and it still needs a terminator, and it still needs to talk to all available ICDs. Well, using the trampoline is not that big of a deal. We can define a generic trampoline, and we can use the tail call optimization for our builds, and it pretty much skips over that. No big deal. The problem comes in the terminator. Because we don't know what the parameter list is, what the return type is, and what ICDs may or may not support that without doing a lot of additional work, it's hard to create a generic terminator for an extension. Because of that, we actually filter out any unknown extensions that are instance extensions. So if an ICD or a layer says, hey, I support this new instance extension bkfoo, and the loader doesn't know about it, we actually strip it out of the list before returning it on a vk-enumerate instance extension properties call. Likewise, we'll throw an error if you still try to use it. Like, I know this NVIDIA driver exports this extension. We will throw an error when you try to use it during create instance. You can disable it with that environment variable there. Just set it to a non-zero value, and it will disable the instance extension filtering. But again, beware, because the loader doesn't know how to handle this, it can crash if you use a forced on extension. To help mitigate this, we've modified the loader so that, one, we update the header in XML very frequently. We try to do it about once a week. So we're pulling in the new extensions from the Vulkan header pretty often. Additionally, we've modified the loader to automatically generate the extension code. In that way, we can get the new extensions out pretty quickly. And hopefully the overhead of, this unknown instance extension doesn't cause problems. The good news is the vast majority of extensions that the Khronos defines are device extensions, and you won't run into this problem. But if you're interested in looking at the script that generates the loaders portion of the extensions, you can see it right here, and just go look on the GitHub at it. Okay, if you're still awake, I'm now getting to hand you off to Lenny, and he will take you from here to the end.
Thanks, Mark. All right. So the next thing that we wanted to cover is the way that the loader interacts with your drivers, or ICDs as we tend to call them. Your drivers are provided by whoever makes your graphics card, NVIDIA, AMD, Intel. It's worth mentioning it doesn't have to be a graphics card, it's just whatever your Vulkan device is. So this could also be whoever makes your CPU. Vulkan drivers have a JSON manifest file. Mark mentioned this briefly earlier. Your drivers are responsible for putting this into your system and for setting this up so that the loader can find it. We're going to go over most of the points on how drivers interact with the loader, but if you want every last detail, you're going to have to look at the loader and interface document that Mark mentioned, which is in both GitHub and the SDK. So the first question the loader has is how does it find your drivers? And we've attempted to pick fairly standard system locations for where this is. On Windows, that means that we look in the registries. You can see the address given on this slide. And on Linux, on the other hand, Windows just, or not Windows, the loader just searches certain file paths on your system. Each of these is aimed at being fairly consistent with the general design of the system. So this part is platform dependent. Like we mentioned earlier, manifest files do not exist on Android. So there's a Windows and a Linux way of doing this, but no Android method. This is an example of an ICD manifest file. As you can see, it's actually quite simple. The first field is just this file format version. That's a version of manifest files so that we know what features are supported in the JSON file. This isn't actually unique to the ICD. That file format version is included in not just ICD manifest files, but also layer manifest files. This next section is all of the data that's specific to the ICD. We start with the library path, which is just the location of the library. It can be provided as either an absolute path, which is what you see here, or as a path relative to the location of the manifest file. We also provide an API version. The API version is just the version of Vulkan which the driver supports. It does not have to be the latest version. It does not have to match what the loader supports. It just lets us know what the driver supports. On Windows, those manifest files are found through the registry, as we mentioned. This is a screenshot showing some example registries from the Windows regedit tool, which allows you to manage registries. You can see that the name of each registry item is simply the file path of the JSON file. Now what we do is we set it to a D word, and by default we set that value to 0. 0 means that the driver is active. However, if you want a quick way of disabling a driver, you can just set it to 1. This tells the loader that you don't want this driver to be active, and the loader will ignore it. This can be really useful when you want to debug something on a given driver, or you want to make sure that a program uses a given device, or really anything like that. In addition to the methods we mentioned of locating drivers, we also have an environment variable which is called vkICD file names. This environment variable overrides whatever is in the previous paths or in the registries to allow you to specify one or more ICDs. So if you set this to one ICD, it will only use that. You can also make this a list of ICDs. On Windows, it would be a list separated by semicolons. On Linux, it would be a list separated by colons. And the loader will only use the ICDs that you specify with this environment variable. The intent is that this allows you to debug with a certain environment variable, or to debug with a certain ICD, and you can easily change which ones are active at a given time. So in addition to the manifest files, the loader has to interact with the ICD through a couple of functions. There's 3 functions of importance here: a negotiate ICD interface function, as well as get instance and the physical device proc address functions. The loader looks for manifest files either when it's enumerating instance extensions or when it's creating an instance. So that's exactly when these values have to be set. Once the loader goes and looks for these, it has to negotiate an interface. Well, what we mean by negotiating an interface is that we have a versioned interface with the drivers. And every now and then something new comes up, we have to update it, so we bump the version. As a result, what happens when the loader loads into the driver is it calls this ICD negotiate loader interface version function. The loader passes an interface version number, which is the version it wants to use. It doesn't have to use that, however. If the driver looks at that version and says, I can't support that, but I can support this older version, then the driver will change what's in that version field and return success. If the loader says, I can't, or rather, if the driver says, I can't support that version and I can't support an older version, it'll just return that you've got an incompatible driver. So this allows us to use a new loader with an older driver if there's a need. You can often use a newer driver with an older loader, but there isn't a guarantee that you can do it because the driver may not support the older interface versions. Like we mentioned before, there's the loader and layer interface file if you want to get every little detail. It's also worth mentioning that in GitHub and the SDK, we have this vkICD.h file. This provides the prototypes for these functions, and it's useful for the driver vendors themselves when they're writing this stuff. So if you actually want to see exactly how this stuff looks in code, that's a very useful file to look at. The next thing we wanted to go over was the way that the loader interfaces with layers. Our goal here is really to keep the layer interface similar to the driver interface. So as much as possible, this section is actually going to look fairly familiar because we've largely just tweaked the way that the loader interfaces with the drivers. So we've mentioned earlier that there are both instance and device properties throughout Vulkan. There are also instance and device layers. In vkCreateInstance and vkCreateDevice, there are these fields with an enabled layered count and the enabled layer names. This allows an application to easily enable layers at runtime. The application can also queue up through Vulkan what does and doesn't exist on a system beforehand so that it can choose programmatically what to enable. I mentioned that we have instance and device layers. That was true, but it's not entirely true anymore. What we found over time was that device layers don't have a ton of use because they only run on a single device, and you pretty much want to run layers on all of your devices throughout the API. So as a result, these two fields, enabled layer count and enabled layer names, should just be set to 0 when you're creating the device createInfo struct. The reason for that is, since device layers are deprecated, the loader's just going to ignore them. If you set those, it shouldn't cause any actual problems, but it's still just best to set them to 0. So as a result, everything we talk about from here on out is going to be specific to instance layers, which are now the only type of layer around. There is still a further subdivision between the layers. We have both implicit and explicit layers. The difference between this is that implicit layers are enabled by default. They don't really tell the application beforehand. They don't request permission to activate themselves. They just get activated. They can be disabled, but rather than explicitly enabling them, you have to explicitly disable. Each implicit layer has an environment variable that can be defined in order to disable it. The environment variable is specified in the layer's manifest file. We'll cover that slightly more in the future. The other kind of layer is explicit layers, and this is what seems a little more natural because an explicit layer is not enabled by default. if the program or the environment enables it, then you'll have it, but only if you explicitly enable it. And we've mostly been covering the desktop loader here, but on Android, only explicit layers exist. Implicit layers are not a thing on Android. So anything specific to implicit layers here is unique to the desktop loader. This is an example of a layer manifest file. It looks similar to the driver manifest file, except there's a good deal of extra data. This first item is that same file format version that we mentioned in the driver. This just specifies the version, and then everything in here is what's unique to the layer. Because the file format version is shared, and then we have these layer and ICD sections, you can actually put a layer and an ICD, or multiple layers and multiple ICDs into the same manifest file if you want to do that. It's worth mentioning NVIDIA actually does this in their Windows drivers right now. They have one manifest file which includes both their driver and the Optimus layer that they ship with their drivers. So in this layer block, we have a bunch of new fields. The first is the layer name. This is just your identifier that you use all over the place to refer to the layer. So when you enable a layer in programs or through an environment variable, this is the name that you have to use. The type given here can only be global and instance. This field used to have a lot more value back when we had instance and device layers, but because we only have instance layers now, it doesn't really mean a whole lot. You're just going to want to set it to global or instance. If you do set it to device, then your layer will just get ignored. The library path allows the loader to find the actual library which the layer is contained in. Like the ICDs, this can be either an absolute path or a path relative to the manifest file. Next is the API version. This is the version of Vulkan that the layer is written against. Again, what's actually being run doesn't have to match this exactly. This is just what the layer is known to support. We also give an implementation version of the layer. This allows an application to look at different versions if there's a breaking change. So when you enumerate layers through the application, you can see not only that this layer exists, but you can see which version. So you can specify in your program, oh, we only support version 3 and later. If it's earlier than that, don't load the layer. We also offer a description field, which is just exactly what it sounds like, a description of the layer. And then we have this functions block. The functions block specifies the name of vkGetInstanceProcAddress and vkGetDeviceProcAddress. If you don't specify this block, that's fine. It will just use the default names. However, if you want to define multiple layers in the same file or a layer and a driver, it's useful to rename these functions to something else. So if you do rename the functions in your library, you have to specify what the names are in this block. Here we have a sample implicit layer file. You can see it looks almost exactly the same. The primary difference is actually where it's stored, not anything in the manifest file. However, there is one difference which you see right at the bottom. It's this disable environment option. This is where you have to specify an environment variable that allows you to disable the layer. You can also specify an enable environment, but this isn't as important for an implicit layer because these layers are enabled by default. So the layer manifest files are located in very similar locations to the drivers. It uses the Windows registries on Windows, and it uses certain system paths on Linux. These paths are actually identical to the drivers except for the very last fields. The drivers are found on Windows registries, they're in Vulkan/drivers. Implicit layers are Vulkan/implicit layers. explicit layers are Vulkan/explicit layers. So as a result, all of these items are actually located right next to each other in either the registry or the Linux file system. So you can find all of them pretty easily since they're together. Much like the ICDs, we have a couple of environment variables which allows you to override the default behavior. The first of these is called vkInstanceLayers. vkInstanceLayers allows you to enable certain layers which the application does not enable as part of it. So this is another list separated by semicolons on Windows or colons on Linux, where you can specify just one or more layer names. These layers will be added to whatever is defined by the program. So if the program decides to enable API dump and you set your environment variable to enable vktrace and standard validation, all three of them will actually be enabled. The other environment variable here is vkLayerPath. This simply forces one or more paths to be used when searching for layer manifest files. This overrides the behavior that is found from the registries or the system paths. So if you set vkLayerPath to the address shown here, an alpha SDK that we have, then the layers will only come from that SDK path and will not read the registries or any system paths. vkLayerPath is a list just like all of our other lists, and it can be set, and in this case it overrides what the default behavior is as opposed to vkInstanceLayers, which adds it. But when you're enabling layers, there's still the question of what order you want to load all of these layers. When you've got layers of the same type in one list, we simply use the order you defined them in. But since there's different types of layers, you have to specify which types of layers get loaded when. So we load implicit layers closest to the application. Then we have explicit layers specified by an environment variable, and then an explicit layer specified by an environment. We do remove duplicates, and just the first occurrence is added. So as a result, if you have multiple implicit layers, those go in first. Then you do the environment variables in the order that the environment variable specified them, and then the application explicit layers in the order that the application specified them. This can be relevant when you're doing things like wrapping objects in a layer, sometimes, or if you modify any data. If one layer modifies any data, then a layer closer to the application will see the modified data, whereas a layer closer to the ICD will see the data that has not been modified. Much like the ICDs, the layer interface is specified in this file that we keep on bringing up, loader and layer interface. And we also have a header here which has the information about layers. It's called vkLayer.h. If you want to write a layer, this is what you're going to want to use. You'll include this file. So poking through this file is really useful if you want to see the details of how all of this works in code. We mentioned there is a negotiation interface. It's similar to the ICD, though we used a model that mimics a little more closely the actual Vulkan spec so that this looks more familiar. We define this function, negotiate loader layer interface version, and it comes with a struct. The struct looks like most of what you have in Vulkan. There's really it comes with a version field and three extra fields rather, which are all closely related. In addition to negotiating the interface in the same way as the driver, we just pass the instance proc address, device proc address, and physical device proc address functions as parameters in this struct. This is different from the driver where those were separate functions. This allows you to do your entire interface through a single function rather than having to specify several. But it works the same way where you pick, the loader asks for a version and it spits it back, and they negotiate, which is described a little bit more here. The loader asks for a specific version, the layer decides if it can support it, and it can either try to bring it back at a lower version, or it can just say it doesn't support that, in which case the layer can't use. If the layer doesn't fill in the function points, the loader can still get them, assuming they use default names, but they have to be using the default names. You can't override those names. Also, we have general security concerns. Mark touched on this briefly, but we try to make sure that the loader stays secure. The loader is just a user mode DLL. It doesn't require escalation, and it has to be loaded in by another program for it to do anything. The manifest files help with security, and we also just run a bunch of tests on it to try to make sure that this isn't going to cause security problems. We run Valgrind verification regularly. We do nightly Vulkan conformance suite testing to make sure that this stuff is still working according to the spec and that it doesn't have security problems. When we release an SDK, we also try to run a bunch of our files through virus scanners. Our normal tool is a website called VirusTotal, which just runs your programs through a bunch of virus scanners, 50 to 60 these days. It includes a lot of the big names, Bitdefender, McAfee, Kaspersky. It also has a bunch of small ones. In our experience, we usually trigger something in our installers. Here you see something. We have two small antiviruses triggered our runtime installer. We're not worried about a couple of small antiviruses flagging our stuff, but we do look for any trends to make sure that we're not accidentally releasing a virus. But in general, there is always a small chance that our stuff is going to flag an antivirus just because it works on this low-level system properties. We've included this table just to summarize the environment variables. I'm not going to go over this right now. We really included this so that if anyone's looking over the slides from now on out, you'll have a nice handy reference for all these environment variables in one place. So finally, we mentioned all of this stuff is public. We'd love anyone who wants to contribute. It's great whenever anyone decides to do our jobs for us. Makes life easier on us. But if you have some feature that you think needs to get done or some bug that needs to get fixed, we're always busy. We're always trying to get to whatever these problems are. But if you can do it yourself, that's the best thing we could ask for. So thanks. That's the end of our presentation, and I guess now it's time to open it up to questions. While we do the questions, I'm just going to leave it on this slide. These are just some useful links, various resources that are quite useful when programming with Vulkan.
All right. Well, thanks so much, Lenny, and also Mark. We do have one question, and Karen or Erica, do you want me to just turn this over to you to take over the questions, or would you like me to read the question for you for Lenny and Mark to answer? Okay, great. All right, so we have a question for Victor. He says, how does the trampoline handle return values and mutability of layers during the call chain?
I was muted, sorry. So the trampoline actually is optimized with the tail call optimization many times, and so it will pass through as much as possible directly onto the first item, which is a layer typically. The return type is just handled by that. The nice thing is most of the commands are already implemented to some extent by the loader, and the core set of them are already exposed, so you can link directly to the, or you can just use, for example, vkQSubmit without having to do a git ProcAddr. So it's all hooked up already, but the fact that the layers come and go, that's all handled by the loaders, and it's because we set up layers at create instance time. By the time you create you get an instance call chain for an object, or you get a device call chain, the layers are no longer mutable. They don't come and go anymore. They are well defined. So you would have to either create a new instance to create a new set of layers, or you would have to destroy your current instance and start again. So everything is pretty much baked by the time you call vkCreateInstance as far as layers go.
All right, thanks, Mark. Another question. This is from Yike, if I pronounce that correctly. On Windows, we can use vkICD file names to locate manifest file, but it seems that the same environment variable does not work on Linux. Can you comment on that?
It should work. If it doesn't work, it's a bug. Please file it. Actually, now that I'll make a note of this and check into it after this meeting today. It should work. In fact, we have one of the guys here locally who intentionally uses it during his testing of the SDK. So if it's broken, then it's something we need to fix.
Can you review again how is it that someone could submit a bug?
Sure. So if you go, if you look at the links here that Lenny is still showing, the very first page link there is the GitHub. And so if you click on the GitHub and it opens up, there's going to be towards the top an issues column. And you just click on the issues link, and there's under that a create issues button that you can choose. And as long as you fill in enough information, I would recommend that if you suspect it's a loader issue, like the issue that is being referred to here, I would just put loader : and then what the issue you're seeing is. And that's pretty much a cue to Lenny or myself to say, hey, there's a loader bug here we need to look into. And we've been trying really hard to at least jump on a bug within a day of it at least popping in. So we try to be very responsive.
Well, we don't have any more questions submitted by the viewers. Is there anything else that you guys wanted to add?
Well, I would just say that one of the things that I think we should mention is on implicit layers, you have to define the disable environment variable, or the implicit layer won't even be loaded. It's a requirement for the implicit layer to have a mechanism to be disabled. Lenny kind of touched on the topic that there are the ability to also define an enable option for an implicit layer. And that's useful for something like, I don't know if any of you are aware of RenderDoc. RenderDoc is a tool, and they have an implicit layer, but they actually leave it disabled by default. So until they define the environment variable to say, hey, turn on RenderDoc, it is ignored because it has both the enable and disable environment variables. And the benefit there is if you know you're going to need a layer at some point, but you want to be able to turn it on and off at will, let's say, hey, I know today I'm going to need it, but in general I'm not, that's an option that you can do. Again, refer to the loader and layer interface. I mean, we mentioned that several times throughout the meeting. If you have any questions, hit that loader and layer interface doc. Lenny and I spent a lot of time rewriting it and trying to make it pretty easy to use. And again, if you have any questions, either file a bug or just pop in a question at email. I mean, you could probably find me in GitLab. I guess they don't have emails in GitHub, but file an issue and we can try to get back to you.
Yeah, and it doesn't actually have to be an issue on the loader. If you read the document and you say, I can't understand that, feel free to file an issue against the document as well, because we might not have written it perfectly.
Oh, sure you did. Okay. All right. Well, thank you so much, Lenny and Mark from LunarG, for this presentation, and thank you to all of you who dialed in. We will have a video online probably in a few hours. An email will go out to everybody who was on this call telling you where to get that. Thank you very much. Bye-bye, everybody.